Heiko Dietrich. No. Was giving from Monash University in Australia.
Yes.
Yeah. Was giving a talk on computing canonical labelings for finite solvable groups.
All right, thank you very much. And yeah, thanks to the organizers for allowing me to speak here, because the topic is a little bit tangential to the things we've seen earlier today. Although on the other hand, it nicely sandwiches today's talks by having Monash presentations on finite groups. In this regard, it's actually a nice sequence. Also, Jesus mentioned it, I should say there's some good news. When I submitted the talk, I didn't actually ask for 1 hour slot, so my talk is actually meant to be shorter. It's good, right? On the bad side, it might feel like an hour, but hopefully not. So I try to start very, very gentle. In the middle part, there might be some technical bits, but you know, it's enough to just understand the conceptual things that are happening. And then at the end, I just show a couple of slides with code and then runtime. So it's very easy going, hopefully. Would also point out that this is joined with my colleagues Santiago Maria Acevedo from La Trobe University in Melbourne and Max Horn from Kaiserslautern Sandau in Germany. All right, so canonical labelings, what is this? So as I said, I want to have this result in a broader context. So let me start by talking about canonical labels. So basically what this is, it's you assign a label to an object such that two objects are equivalent in some sense, even only if they receive the same label, right? And of course, we've all seen these things. For example, earlier this morning in Melissa's talk, we've seen that if you talk about equality of elements in permutation groups that have base, you know that this is true if and only if those elements have the same base images, right? So instead of storing the whole large permutations, it would be enough to just store the base images, and this is a canonical labeling for deciding equality. Homeomorphism of compact orientable surfaces, of course, this is the genus. Similarity of square complex matrices, well, here you could just look at the Jordan normal form, for example. Equality of vector subspaces, well, I should say maybe finite dimensional vector subspaces. You could look at a reduced row echelon form of the basis. Isomorphism of semi-simple D-algebras over C, well, again, finite dimensional. You could look at the Lincoln diagram. Isomorphism of graphs, well, this is probably where canonical labelings showed up. First of all, you know, there's a whole theory about canonical graphs, where you find a canonical label version of a graph that uniquely determines the isomorphism type. It has had lots of applications in algorithmic context. There's a node here, traces package by McKay and Piperno, and lots of other people have worked on that. So it's a very famous area where canonical labels show up. And in this regard, I would also like to mention the work of Schweitzer and Liebking. They presented a paper in Stock where they present a uniform method to canonize combinatorial objects. So they talk about graphs, hypergraphs, codes, even permutation groups up to permutation isomorphism. So it's a very interesting piece of work. Okay, so I'll be focusing on groups. And what would be good labels for group isomorphism? So labels for groups that decide isomorphism. Well, it depends on your classes of groups you restrict, right? If you look at cyclic groups, for example, we all know that for every size, there is a unique isomorphism type of that group, which is cyclic. So the size uniquely determines that isomorphism type. If you look at groups of size p times q, both being primes, distinct primes, then basically there are at most two types of groups. It's either the cyclic group or if p divides q minus 1, and you have non-trivial action, then there's one other split extension of those groups that's not obedient. So essentially, you just need to look at the size of the group and the size of the commutator subgroup, for example. It tells you uniquely the isomorphism type. In general, for finite abelian groups, we have the abelian invariants. Again, it's a list of integers that divide each other and so on and so on. And this list uniquely determines the isomorphism type of your group. Why is this useful? Well, if you have a list of groups in front of you and you want to decide, you know, which of these groups are isomorphic, well, you could just test every pair of groups until you've decided that. But unfortunately, group isomorphism is a very complicated and difficult problem in general. It's a very costly problem. If by some means you can compute labels for all these groups, then you just have to compare the labels. And labels are usually much easier to compare. Right? So if you have a long list of groups, it's much better to first spend time to compute labels and then compare these these labels. So there are in particular questions of complexity and practicality. Well, complexity because essentially this does solve the isomorphism problem, right? And it's a difficult problem, and people have spent a lot of work on trying to find the complexity of group isomorphism. So this is definitely very interesting to investigate. We don't focus on complexity here. To some extent, it's a stronger problem than isomorphism testing. We only focus on practicality. And what do I mean by that? Well, I would like to have something that we can implement in a computer algebra system, and that allows me and others to use this and compute canonical labels for certain groups in a reasonable time. You can't expect this works well for all groups because it would solve the isomorphism problem, but hopefully it does work well for some classes of groups that are of interest. So that's the idea. Let me give you one first example of group labels that decide isomorphism. It's ID small group. It's particularly relevant in practice. It stems from work of Ulrich Beschel, Bettina Eick, and Eamon O'Brien, where they presented algorithms that construct the groups up to isomorphism of order at 2000, not excluding 1024. And they've implemented that in computer algebra systems, and it's available in GAP and Magma, for example. And as I said, it provides a database of these groups up to isomorphism, and also canonical labeling. So you can give it a group of size that's covered by the database, and you ask ID small group, and it returns hopefully a number, n, I, that says, well, this group has size n, and it is isomorphically ith group in the database list of groups that is provided. So this database-based group, this is fixed. Right? It's complete, it's fixed, it's deterministic, and it tells exactly to which group it is isomorphic to. So if you know this number, you know exactly the isomorphic type of the group. And just to give you an example, so this is using GAP. Not sure if everyone's aware of GAP. It's a computer algebra system. You can compute with groups. So I've constructed 5 groups here. First one given by generating permutations. Second one is just the symmetric group on rank 3. Third one is the matrix group GL22. Fourth one, the Hydra group of size 6, and the last one, the cyclic group of size 12. You all know that these are partitioned into 2 classes of groups. If you ask GAP to compute the ID of these groups, indeed, you see that the first 1, 2, 3, 4 are all of ID 6, 1. So they're all isomorphic. They are the unique non-abelian group of size 6. And the last one here is the cyclic group of size 6. Right? And you can also go the other way. You can ask, well, what is the first database group in the list of groups of size 6? And you get a group back. And you can then construct an isomorphism and see that this works. So it's very, very handy when you work with finite groups computationally. Yeah? So it's very useful to be able to construct these groups and also to identify these groups quickly.
So has the number 2000 increased since 2002?
And I think officially not there. I mean, I will mention there's other when I come to that. So how does it work? Well, the database of groups is given by a database that constructs these groups using presentations or generating presentations. And if you want to identify a group, you basically just compute some invariants and see, which of these groups is it isomorphic to. Just to give you an example, if you look at groups of size 1010, what you have to do is you compute for your given group the size of the commutator circle and the size of the center. And there are only 6 possibilities. This pair is one of these 6 numbers, and depending on what number you observe, you know what group this is isomorphic to. Yeah, so you just compute some invariants of the group, and then based on the known classification, you know exactly which group in your database this group is isomorphic to. For size 6, you just have to check whether the center is trivial or yes, we saw it. Now, I should say that in general, the invariants that are used in the database are much more elaborate. I mean, here we have 6 isomorphism types of groups. It's rather simple to distinguish the groups. And just to witness that, Bettina Eick and Hendrik Schanze, Bettina's PhD student, they put something on the archive where they tried to identify the groups of size 2 to the 9. And there you have more than 10 million groups. Right? So for 10 million groups, you can't just compute 5 invariants. That's not it.
Sorry, just to clarify, so for each order that then goes up and looks at this of invariance, it needs to calculate for that order.
Yeah, basically there's a decision tree, right? You have your order and then you have a decision tree. And it's very elaborate. I mean, again, when you look at this, yeah, some work goes into that. And it is worth to point out that this approach of identifying groups is highly non-constructive, right? I mean, I just tell you, well, if you have this pair, then it's this group. You don't have an isomorphism. Right? So if you want to have a constructive identification with an isomorphism, you have to do a little bit more work. But it tells already that you know the shape of the group. And yeah, we'll talk a little bit more about the database. So there are also other families of groups in the database. For example, based on Hölder's classification, there are groups of prime power order up to p to the 4. They are included. For certain small values of primes, also p to the 5, p to the 6 and 7 are included. The family of groups that have square-free order, so no prime square divides the order, is also included. This results basically on the classification result of Hölder, I think, Tassenhaus. And the implementation, I think Ulrich Becher has done it in GEP, and then Slattery also has a paper on that. But Bettina Eich told me that Neuwieser family also thought about this earlier. So these are infinite families, basically, that are also contained in the group database. And there are other small order types also included, but if it's about an upper bound on the number of the sizes that all groups are contained, I think 2,000 is still the upper bound at the moment. I think there has been some work to extend it to 20,000, but it's not published yet. Okay, I should also mention that a couple of years ago, myself, Bettina Eich, and my PhD student, Eileen Pan, we have extended the database by the groups of these sizes here for arbitrary primes, P, Q, and R. And these groups have been considered in the past in sometimes very unreadable papers. I mean, they're very old and sometimes very hard to digest. So we basically have redone the classification and use different methods to get these groups, not to the actual small groups database. It's a different package that ends the functionality. And yeah, how to do this? Well, groups of order p to the a, q to the a are solvable by Burnside's result, and they have a pseudo system, so they're always products of pseudo subgroups, and then you can make a case distinction on whether a pseudo subgroup is normal or not. And alternatively, what is used for the last case is a fitting approach where you look at the quotient for the fitting subgroup, which in this case always faithfully embeds in the automorphism of the fitting subgroup. So you do some case distinctions and eventually get the classifications. But also we got identification function. Yeah? That's quite useful. And I should say that it gets a bit more complicated because you just don't compute some invariance. You basically what we've done here is we sort of try to recover the presentation of the group in the data tracks. And this means technically it's almost constructive because if you find generators that exhibit the presentation that you have, find basically an isomorphism. So this is one of the aims that we want to add isomorphisms there as well. And further extensions are work in progress. I'd like to mention that. So it's basically part of a project that Bettina Eich and I have. It's a small grant that allows us to travel back and forth between Australia and Germany. And this is more or less the topic of that grant. So we want to extend this to groups that have at most 5 prime factors. This is joined up with a number of people. There are more cases, and it's a bit more delicate. The case of prime power order p to the 5 is separate because there are difficulties, and this together with Henrik Schanze, whom I mentioned before. And I mentioned this p to the 5 bit also a little bit later because it's relevant to my main topic. And then there is also a project that is currently on hold, cube-free groups. So I did some work on cube-free groups earlier together with Bettina Eich. So there's a lot of structure theory known for these groups, and they're together with Melissa Lee and David Jeffries. There has been some progress in order to get some sort of identification and construction up to isomorphism. But yeah, so we need to keep this up, pick this up again sometime later. Anyway, so these classes of groups are getting more and more complicated. And in some of these classes, you don't really have already lists of presentations in front of you, which raises some questions. How can you find identification and construction? And if you want to say, oh, I want to construct the 17th 50,000th group of order blood. And you need to have some canonical ordering that allows you to go there, right? So usually you need counting functions that tell you how to get there. For some of these classes, it's getting a bit more complicated because you might not have this information available, right? So what can we do in these cases? And a very good example here is P groups. P groups, groups of prime power order, there are a lot of that. We've already seen there are more than 10 million groups of size 2 to the 9. Right, so how do you construct the 7 million group 350,512, right? So you need to have some very good idea to get there quickly. You don't want to construct 10 million groups and then go to the group you're interested in. You want to go there directly more or less, right? So you need to bucket your groups into some partitions and quickly go into the bucket that you're interested in, which means you have to have counting formulas and so on. So there are many P groups, and nevertheless, there's also very good algorithmic functionality to work with P groups, all based on P group generation algorithm. I give more references later, but here let me just say it started with McDonald, Habash, Newman, and O'Brien, and it allows you essentially to construct all groups of size P to the n up to isomorphism in an iterative process. Well, of course, in practical terms, you can't because the number of groups is just too big, but in theory, this works. And Eamon has utilized this algorithm to describe basically a canonical presentation for P groups. Right? So if you have a P group, then you can try to reconstruct this P group using that method. And while constructing it, you make canonical choices. So you build up a new group that's isomorphic to the given one, but you get a group that's canonical. So what does that mean? It means the structure of that presentation only depends on the isomorphism type you start with. So if you have two isomorphic groups, and you do this construction, you end up with the same group presentation. So let's call this canon of G here, canonical presentation. So two P groups here are isomorphic if and only if they have exactly the same presentation. An example, look at an elementary abelian group, say of size P to the R, so it's a direct product of R copies of the cyclic group of size P. This would be one group presentation with R generators and with these relations here, right? So this would be a canonical presentation for the elementary abelian group of size P to the R. And again, if you then compare canonical presentations, well, you can just consider this thing as a string, right? It's a string of symbols, and you just compare whether these strings are equal. Here's an example. Let's look at the pseudo two subgroup of Sim6 and the direct product of C2 times D8. Again, in GAP, we load the package NUPQ, which provides a lot of the functionality of the NUPQ algorithm suite. We construct those two groups, A and B. And I highlight the important command here, and ignore the rest really. So there's a command epimorphism standard presentation, which computes the epimorphism on that standard presentation. And it will be an isomorphism in this case because the groups we started with are P groups. So we get two groups which are stored in the list CAN. And when we look at their relators, the relations of those two groups, you see it's exactly the same list of relations. So the canonical presentations of A and B are really the same as this group presentation. Equal. It's great. And even better, every group presentation that has a nice form, and I come to this later, for the cyclic presentations, you can basically encode this presentation as a single number. You can do this anyway, but there's an efficient way to do this that's provided by the function code PC group. I think it comes from the paper of Bettina Heike and Hans-Ulrich Becher, which gives you just a single number that encodes that presentation together with the group size. So if you have the code size, uniquely encodes the group presentation, and therefore so it's a very nice way to encode that group by single number. So actually pair of numbers, you need the size. So the approach in a nutshell. So again, this might be one of the more technical slides. I just want to give you the idea of how this works in one slide. The idea is to take your P group and construct a certain subgroup series, the so-called lower P sample series. It's the fastest descending series such that each consecutive sections are elementary abelian and central. You can construct that. And then the idea is you construct an epimorphism onto the first section, which is elementary abelian. And this can be done using known abelianization algorithms. So it's very, very efficient. And then we just do this iteratively, right? You have an epimorphism on on the quotient modulo pi, and you want an isomorphism on the canonical form of the quotient of I plus 1. How do you do this? Well, suppose we have the canonical form of G modulo pi given by a presentation. What you do is you construct another group called the P cover. This is H star. Don't worry about how this is constructed for now. There's another group, it's bigger. And then it's known that the group we're interested in is actually a quotient of that cover. And it's a quotient of that cover by a normal subgroup that lives in another well understood group and with a certain property. And then the idea is, well, there are many choices for this normal subgroup. Let's just pick a subgroup that's sort of canonical among all these subgroups. M is in fact a vector space, so we are talking about subspaces here. And we can canonically order subspaces, as I mentioned on the first slide. So this is one way to pick a canonical object. And I should say that canonical here really just means, it doesn't necessarily mean that a beautiful element is just canonical in the sense that it's deterministic and only depends on the isomorphism type of the input. Well, then you define your group, your canonical group, as the quotient by that canonical subgroup. So that's basically the idea. It's rather easy to describe. And eventually you have a canonical presentation of that group. However, even though the description is very short, actually a lot of work went into the development of this algorithm and making it actually efficient. So I'm not sure if I covered everything, but this is definitely going into that. So first of all, you need to describe how can you work efficiently with these groups. So you need special presentations, weighted polycyclic presentations that allow you to compute with these groups in a rather efficient way. And see the number of people that were involved here. And Eamon almost shows up everywhere. So there's quite a bit of work. Then if you want to work in polycyclic groups, I mentioned this later, you have an efficient group multiplication. This goes back to studying collection algorithms, where many people have been researching best ways to do that. And then there's the whole ANUP quotient algorithm suit by George Habersh, Newman, and O'Brien. P generation, I mentioned before. P group isomorphism, I mentioned before. You talk about polycyclic presentations. You have to check consistency of these presentations. So this is its own interesting topic, how to check consistency efficiently. And then also along the way, you have to work with automorphism groups for finite P groups. There exist bespoke algorithms that allow you to do this efficiently. So also work again with AIM. And there's a 2006 online tutorial, I think, where Eamon said that the original program contained more than 22,000 lines of code. So it's just an indication that it's not just 100 lines of code implementing the previous idea. So a lot of work and effort went into making this efficient, and it's really, really powerful. For example, Eamon and Michael Gordon-Lee, they've used it to compute some restricted turnside of incredibly large size. They've determined that the group R27 has size 7 to the 20,460. So these algorithms can be used to do like really big computations with very, very large groups. However, canonical presentations can actually also take time even for small ones. Remember, the talk title is Canonical Presentations. So I just want to set the expectations in terms of runtime. So here I have 3 groups of size 11 to the 5. And when you compute the standard presentation of these groups, in GAP takes less than a second, 4.5 seconds, and then 26 seconds, which, well, it's still okay. It's just maybe more than you would have hoped for. And the difficulty this computation is not so much the size of the group, it's really the size of the Frattini range and upcoming modules that you have to study and work with during your construction. So so I mentioned this because we will now look at finite solvable groups, and of course every finite solvable group, every finite P group is also finite solvable, and we have to keep this in mind when we think about, okay, what can we expect in terms of runtimes and efficiency. But before we do that, you might remember that I said that between Heiko, Chancellor, and myself, we work on P to the 5 identification, right? So let's do a quick interlude and give an update on what's happening here. So it's really just work in progress. But what we do is we provide group identification of groups of order dividing P to the 5, and hopefully also isomorphism soon. So it's on the way. And if we look at the 3 groups I just mentioned to you earlier, if we apply our function IDP5 group, we can do the whole lot in 37 milliseconds. And only one isomorphism is constructed so far for the second group, which took 4.5 seconds here. So we, again, as I said, we first focus on identification and isomorphisms come later. But it's really fast because we use very bespoke methods to deal with these groups. If you look at all groups of size 31 to the 5, and like random copies of those, there are 131 groups. We can do this in 26 seconds in total, which is 200 milliseconds per group, which again is pretty good, I guess. Some of them have isomorphisms attached, and here you can see that the isomorphism has an image that is really having the right group ID that's in the database. Or I should say, there is a construction algorithm in the database. So you can construct groups of size p to the 5 using the GET database, but no identification. So we want to fill that gap here, which annoyingly means that we have to identify the groups in the database. It's really bad because when we have redone that, we get different descriptions, and then we have to match it to the groups in the database. That's a bit annoying. But even for smaller powers, like here we have 433 to the 4, we do actually pretty well. So we can identify, the gap functionality, which is already available, needs like 6 seconds to identify the group. And if you ask for constructing an isomorphism of p groups, well, I basically aborted it after 10 minutes because I was too impatient. If we use our code, it takes half a second. So again, it's a great improvement for these small p to the 5. All right, so now let's go to solvable groups. Canonical presentations of these. Why? Well, all nilpotent groups, finite nilpotent groups are just direct products of finite p groups, and these can be dealt with p group standard presentation. Right. So the next interesting class of groups are maybe the solvable groups. There are many solvable groups by the odd order theorem. Every group of odd order is solvable, right? This will cover quite a bit. But most importantly, I guess, is that we can compute very well with finite solvable groups to some extent, because these are exactly the finite fully cyclic groups. And to give you a little bit more details of what we do, I just very briefly recall what a polycyclic group is. I mean, as the name says, polycyclic, it means that there is a subnormal subgroup series such that each section is cyclic. Okay? And we just pick a representative element that gives you a generator quotient here, let's call it GI. And the size of the cyclic section, because finite group, let's call it RI. So we have a what's called polycyclic generating set, all these guys, the blue guys, and we have these so-called relative orders. All right. And the linear induction allows you to show that every element in the group can be written as a normalized product. It's a product, an ordered product, G1 to some power up to Gc to some power. And these powers are all bounded between 0 and your relative order. A very nice normal form. If you look at Gi to the Ri, or a conjugate Gj to the Gi, then these guys by construction live in Gi plus 1. They have normal forms. Let's call them Wi and Wij. Then you get some relations between those generators, right? And these are the only relations you need to know in order to write down the group presentation, right? If you just write down these relations, you get a group presentation that's isomorphic to the input group. And you can work very well with this group presentation because these relations tell you exactly how you can normalize every group element. This is called basically a collection. If I write on an arbitrary product in my generators, you can do these relations, we bring it in normal form. This would be called collection. But it's a very useful, efficient setup to compute with groups that are finite and solvable. Okay. So the first question maybe is, it's a very naive question, and once you thought about it, it's actually trivial. Do actually canonical representations exist? Right? So if you have a solvable group of this prime power factorized order, then there is a polycyclic presentation that has the sum of exponents many generators, and all the relative orders are primes. Yeah? There are only finitely many polycyclic presentations with this many generators and these relative orders. Yeah? So you can just write down all polycyclic presentations, a subset of these defined groups, a subset of those defining groups that you started with. So you could just pick that one that's sort of smallest in some sense. And it's a trivial observation, really. There is an example. If you look at groups of size 8, every such group can be described by a polycyclic presentation with 3 generators, ABC, relative orders 2, 2, 2, and they are then just parameterized by these 8 numbers, which are all 0 or 1. Right? There are 16 such vectors that give you a group of size 8. And if you're looking for the dihedral group of size 8, then you have 7 of these vectors that give you exactly the group. Dihedral group size 8. So you could then pick maybe the smallest one here with respect to lexicographical ordering. And that could be your parent. Obviously, that's a rather stupid way to proceed. Right? You don't want to look at the set of all polycyclic presentation. But it tells you that these things at least exist. All right. Good. So what's our approach? So similar to E groups, we also consider a subgroup series. And we want that this series has the property that every section, every quotient, iterative quotient, is elementary abelian. Not necessarily central, because it's not important. And we want that whenever you have 2 isomorphic copies of the group, G and G tilde, that every isomorphism maps Ci of G to Ci of G tilde. Yeah? So one way to do this is, for example, to look at your derived series. The quotient, the sections of the derived series are all finite abelian groups, so they're direct products of pseudo subgroups. So you have a section, you can refine that, so each section is a finite P group. And for the finite P groups, you can define a solid elementary abelian section. Right? So this will be one way to. Doesn't really matter too much. But this is all we need really. And yeah, so let's just abbreviate GI going forward for this fixed series. So the construction of this series has to be fixed for the whole process. And then the idea is, well, we first construct our first epimorphism, which is onto an abelian group. It's easy to be done. And then again, we use an iteration. So we have our epimorphism on the quotient of GI, G modulo GI. We then want to describe G modulo GI plus 1 as an extension of our canonical copy times a module that's isomorphic to the next thing. Yeah? And the idea is we want to pick a canonical such extension. You might wonder, well, what about using a cover approach similar to the P group standard presentation? We actually thought about that, and in fact, Alexander Hultgen, I have a paper where we look at universal covers of groups where we consider solvable extensions for solvable groups. And also Max Horn and Tina Eich have a paper where they basically look into these things, especially for solvable groups. But there are some additional technicalities that made us think that the approach that I will describe here is a bit more efficient. So what do we do? Well, we use basically extension theory and tools from early work of Robinson on cohomology groups and group extensions. And we also use work of Smith and Holt, where they, when they constructed automorphism groups of finite solvable, so the compatible pairs and things like that. So extensions have 2 ingredients, and thanks to Melissa for recalling cohomology groups earlier this morning. So extensions have 2 ingredients. You have a quotient group, and then you have your normal subgroup that has the comodular structure, right? And then you have cocycle cohomology class. So let's just briefly recall the modular structure is really just a group homomorphism from your quotient group into the automorphism group of your group. And what will be important for us are the following 2 things. The direct product of the automorphism groups acts on modular structures, and you don't have to worry about the details too much. Just remember they act on modular structures. And secondly, if you look at this action and you look at a stabilizer, that thing is relevant and has a special name. It's called the group of compatible pairs. It's called group of compatible pairs because if an element lies in the stabilizer, it means it's really compatible with your module action. So it means that if you act with D on M and then apply beta, it's the same as first applying beta and then acting with alpha option. So you can move out G basically, but you have to twist it by this automorphism. Okay, these are 2 ingredients that we will need later. The other ingredient are, as I said, homology cocycles. So H and M are given. We have a module structure. Then an extension is, well, it's a group that has a normal subgroup isomorphic to M such that the quotient is isomorphic to H, right? Many ways to realize that. The good news is that up to equivalence of extensions, there's a very nice way to write down these groups. You take as your underlying set the direct product, the Cartesian product of your two input loops, and then your group multiplication looks like this. The first component, which is an H, you just multiply the elements. In the second component, when you move H past M, so you act with H on M using your module structure, then you have M. And if this would be it, then this would just be the semi-direct product. But there's another term, gamma, that depends on GH, and this is a two-cocycle. Again, if you don't know what this is, don't worry, here's the definition. It's basically a map from H times H to M that has certain properties guaranteeing associativity. And also, you can determine when such an extension splits, which again, Melissa explained this morning. This happens if and only if this gamma is what's called a two-coboundary. And these are those maps. And the cohomology group, is the quotient group of these guys, describes all group extensions up to equivalence. Now, the thing is, in general, it's not really easy to work with cohomology groups. One indication is that, for example, two cohomologies, they are parameterized by functions from H to N. So there are many of these guys. Luckily for polycyclic groups, there's a much more efficient way to compute with cohomology groups, which makes the whole machinery work. So I want to briefly explain that. So it's a bit technical, as I said, but I hope you get the idea. So here we have two polycyclic presentations describing our groups H and N, right? And H acts on M, so we also have the module structure encoded by how generators of H act on generators of N. So I want to find the polycyclic presentation of an extension of those two. Right. So how can I do this? Well, I can basically merge those two presentations. So this is just the presentation of H, right? I've just copied the blue part. Now I want a group that has M as a normal subgroup. So I have to add the information from M's, right? So I added the information of M. But if I just do that, what have I constructed? I've constructed the free product of H, which is not what I want, right? I want that M is a normal subgroup. So I have to add the module relators as well. And if I do this, it's exactly the semi-direct product. Right? Now I don't want to construct just the semi-direct product. I want to construct or describe all possible extensions of H by M. So if I have the general extension of H by M, the relations of H hold in the group modulo M. So I need some terms here that live in M. And if I forget about the red part and the module, then I get H back. So this T here is called a tail vector, and these tails are elements in M. So for every choice of elements in M, this is definitely a group. Well, it's a group presentation, so it's a group. The question is, for which choice of tails is this a group presentation? But what I wanted to say earlier is that up to equivalence, every extension of H1 has this form for some T. So if you're interested in describing all extensions, you only have to look at these guys. And the good news is now, you can work with these tail vectors, put this up here, you can work with these tail vectors without knowing Z2, the two cocycles and two cointegers. Basically, there is a group homomorphism from the set of two cocycles into the tail vectors that give you extensions, and similarly for those tail vectors that give you split extensions. And you can compute these essentially using linear algebra. Yeah? So you have to use what's called consistency checks. You treat these guys here as indeterminates. You check what are conditions on these indeterminates so that this group has the right size, so it's an extension. And these conditions give you a linear equation system, and then you solve that. And then you have curly Z and curly B. And the good news is the quotient is exactly our cohomology group. And so you can compute cohomology groups of polycyclic groups very efficiently. And this is the way we want to describe our extension. All right. So the idea is, we have an equimorphism on G modulo Gi. We want the next one, we want to lift it and recall that the group we are interested in is an extension of the previous section by that module. So what do? We use this equimorphism to construct isomorphisms between the G modulo Gi quotient and H in our module. And I have to point out that H and M depend only on the isomorphism type of G. That's canonical. And then we use these isomorphisms to describe the next quotient as an extension of H by M with respect to some module structure and some cocycle. And this module structure and cocycle is what we observe basically in the given group. Yeah, we just read it off. So we observe this. Now the question is, can we somehow modify the module structure and the cocycle to make it canonical? That's the idea. But what about the module structure? What happens if we start with an isomorphic group? We do the same construction with an isomorphic group. Well, the term G modulo Di gives us the same canonical group, by definition of canonical forms, right? So this is equal. And the modules are also isomorphic. It's elementary abelian, or just a vector space. And the observed module structure gives us some other homomorphism, like phi tilde. Yeah? So then you can show that the module structure of G that we have observed and the module structure of P tilde that we have observed, they lie in the same orbit under the direct product of these automorphisms. They are in the same orbit. And conversely, if you pick any other element in that orbit, then this gives you a module structure that could come from an isomorphic group. So we really have to find in the orbit of the automorphism group, of the observed, we have to find some canonical element. And canonical is up to us how we want to define that. Right? As I said earlier, we just have to make it deterministic. So once we have done that, we assume that the module structure is the canonical one. And then the next thing is to find the canonical 2 cocycle. Right? So we observe 1 2 cocycle that gives us the extension. And we get an isomorphism between that group and the quotient we're interested in. And now the question is again, what happens if we start with an isomorphic group? Well, if we start with an isomorphic group, we get some other 2 cocycle, gamma tilde, and an isomorphism between those tilde pairs. But the nice thing is they all map M to that quotient. So eventually we get an isomorphism from E gamma to E gamma tilde that maps M to M. And these are very special isomorphisms. They map the normal subgroup to the normal subgroup of the extension. And the work of Robinson shows how to solve this isomorphism. Yeah? You have to act with a group of compatible pairs, this weird group that I mentioned earlier, the stabilizer. Right? So the thing is, we observe a 2 cocycle, and then we have to look at the orbit under the group of compatible pairs, and in there, take a canonical 2 cocycle. There's a slight technical annoyance. You see here, this is modulo 2 coboundaries. That's a little bit annoying. So we also have to work around this coboundary condition. Again, I brush this under the carpet now, but this is essentially what we have to do. We find a canonical element in that orbit. And once you've done that, you're basically done, right? The idea is we have iteration. First portion is just the could be the idealization. We can construct that isomorphism. Then we iteratively define our canonical extensions using canonical cocycles and module structures. And then when we find these canonical elements, we also find elements that map the given one to the transversal element. And these transversal elements are important to construct the isomorphism. If I go back here, oops. Yeah, so I not only need the canonical 2 cocycle, I also need an element that maps on it. Yeah? And I need these elements to construct the isomorphism. And then at the end of the iteration, you're done, essentially. And the construction really follows, implies that what we constructed is a canonical presentation in the sense that 2 groups have the same presentation, if and only if they have been isomorphic. All right, so that's the idea. Again, similar to P group standard presentation, the idea is rather simple, but getting it work took a little bit of work and effort. So let's maybe comment a little bit on the code. So we have a proof of concept implementation in GAP. It provides basically the main framework, but there are some bottlenecks that we couldn't really address properly. And I just realized I actually do fill 1 hour. Sorry about that. It's like in a lecture when you think, oh, today's lecture is short, I can talk more, and then suddenly time runs out. So again, it's just a bit of code that I will show in the main bottleneck. So the first bottleneck is computing the canonical module action, right? So this is our canonical group. It's given by a polycyclic presentation. Our module action is just a group homomorphism. So it can be encoded by a list of matrices that tells us how the generator is. And we have to determine a canonical element in the orbit where we act with this automorphism. And this is really the main bottleneck. It's very, very complicated to compute this for many, many groups. And I'd like to mention it's a difficult research problem by itself. There's work by Sau, for example, where they talk about canonical forms for matrix towers in polynomial time, where they only act without M. Yeah, so it is really difficult. And it's the main bottleneck. Second thing is canonical tuple cycle that we have to consider. Basically another orbit calculation that we have to do and find the minimal element, right? And also we have to deal with this covariance thing here, which I mentioned earlier. It's also quite technical. And these orbit sizes quickly become unmanageable. So we need some improvement. So we have special algorithms for trivial modules. You can also go along composition series and break down the orbit calculations. There is Ruth Schwingel's algorithm when you have P group actions and so on. And also, we was mentioning Jefferson's, Waldecker, and Wilson's work. They have work where they compute canonical images in permutation groups. And so sometimes we can translate certain operations to permutation group actions and use their algorithm. That works as well. And the third bottleneck mentioned here, we need compatible pairs in automorphism groups. There are get functions that do it. However, during our iteration, we have basically all the ingredients that we need in order to write these down. Right? So we can construct them ourselves, but people that spend a lot of time getting good automorphism group algorithms, we can't compete with that sometimes. So there are some issues to make this a little bit faster. All right, so let's look at some examples. So for Nilpotent tree, we use P group standard presentation. So the first section is assumed to be the largest Nilpotent portion. Yeah. So here's a group of size 1,800. There are 750 groups roughly. If you can ask the isomorphism canonical PC group, it gives you an isomorphism to that canonical group, takes 56 milliseconds. You can get the canonical PC group, and that's the code of that. So this uniquely defines the group. I should say, if we improve this package going forward and have new orbit operations it might be that the canonical orbit representative that you choose is different ones. So if there's a new package version, it might be that your canonical presentation looks different. So if you compare canonical groups, you have to use the same version of the package, otherwise it's not compatible. To give you an example of where it takes a little bit longer, let's look at a group of size 1,296. So here we need 6 seconds already. So this is just showing that bottlenecks are visible, even for small orders sometimes. But there's also good news. So we ran out of the database. There are 33,000 solvable non-Nilpotent groups of size at most 2,000, and we assume there's no large prime power dividing it. We need an average 40 milliseconds to solve this. If we run over the solvable cube-free groups between this range, we need an average 30 milliseconds to solve every group. The worst time was 7 seconds for the group we saw earlier. But if you run over this order on average, we need 85 milliseconds. There are some groups that are just the same, but in average, it seems to be all right. For cube-free, similarly, there's one group where we need 3 seconds, but in average for this order, it was 70 seconds. But now here comes the bad part. If we allow the p to the 5 divides the size, then there are a lot of groups, first of all. If you impose the p to the 6 doesn't, then there are only 30,000 groups. Average time is 100 milliseconds. But the worst case at the moment is 80 seconds, which is really embarrassingly slow. So as I said, it's still work in progress. We look into this, but the thing is there's no method that works well for everything. You have to have some bespoke improvements. And also subtle, we use our own automorphism group construction for that. If I turn this off and use Get's automorphism group construction, which in general is slower, for this particular group, we get down from 80 seconds to 3 seconds. And then the new worst case is another group of 35 seconds. And the problem is the number of generators for the automorphism groups. Because what we do ourselves has more generators. So you see, it's a little bit try and error to get some groups done, but the average times are still okay. So here we run over all solvable groups of size 4, 44,100. We will evidently skip that there. The only thing I wanted to say is that if we construct these, identify these groups, of which we have how many? 3,087. In average 66 milliseconds per group. If we get to identify those groups, takes 105 seconds, and isomorphism testing of just one pair takes 5 hours. So not very great. However, there's an algorithm of James Wilson and myself just for cube-free groups that does isomorphism very fast. So if you add up those times of the existing gap functionality, it's like 218 seconds. We needed 205 seconds. So it's more or less on par with what we've done before. Here's some large cube-free group. Yeah, so we tested random copies here to see that the code is really the same. And if you test it against the other functions, isomorphism groups just fail. So I aborted it after 2 hours. Isomorphism cube-free works well. And the very last slide just shows some other large groups, which I constructed as subgroups of some Reese products. And they have derived length 3, 4, and 6 respectively. And the times are 2 to 3 seconds. So these also worked pretty well. I have to say these examples are curated, as I said. You know, there are small groups that fail, and if you construct probably a random large group, it will fail. But you have to, be a bit less. So the code definitely can be improved, but I think the framework is there. It works well in average for some groups, and that's all of this. Thank you.
Questions, comments? Your code for computing second cohomology groups, is it limited to doing that for solvable groups acting
Yes,
on?
it's actually not mine. It's gap has already code. So
It's already the gap code.
Yes, that's what is one.
I was about to lament how slow the gap code is. Second cohomology groups.
Yeah.
And I was going to ask if you'd done any better.
No, we have done well. I think it's pretty good actually. I mean, at least for the example, that was never the bottom.
Well, if you do it for non-solvable groups, it can be extreme.
Yes, yeah. I mean, this obviously I was just talking about solvable groups, and they're just in their algebra essentially.
Yeah.
Right. I mean, your presentation is akin to a well, you basically want to see when is this thing consistent or complementary lighting system. You just check overlaps, you get conditions, and solve the system basically.
Yeah, in the beginning you said, speaking about another algorithm that is not constructive in the sense that it doesn't really provide an isomorphism.
Yeah.
Do you understand that the rest of this work provides the isomorphism?
Oh no, we have an isomorphism. So basically, what we return here. So we return two things, right? We basically return an isomorphism to the canonical PC group. Right. So the canonical PC group is what I called CanG before. It is that presentation that is uniquely determined by the isomorphism of the group. And here we get not only that group, so the group would be canonical PC group, but we also get an isomorphism onto that group. And so if you have two isomorphic groups, this group would be considered the same. Where there actually is a subtle thing, there are different gap objects, but when you look at the presentation, they look exactly the same. So one way to compare them is to use this code PC group thing, which gives you the number, and then you can just compare the number, and you see it's really the same.
But I think the point is that you've got G and H, and you've got your standard copy. You go from G to the standard copy, you go from H to the standard copy.
Yes.
And hence you get G to H.
Yes, the detour, I understand the copy.